Okay. Good morning once more. So we continue today considering the elements of quantum mechanics. And the next time, I think we will start looking at the moduli space of PSL2R connections. So it is still elements of quantum mechanics. So let me start with recalling the spectral theorem for self-adjoint operators. So there are many formulations of that theorem, and I will give just one, which uses a minimum preparation. So let A be a self-adjoint operator in a Hilbert space. In a Hilbert space H. So then there exists a measure space X mu, and then measure space an isomorphism of Hilbert spaces. Hilbert spaces, so U, which goes from which direction it goes? Yeah, from H to L2 of X mu, and a function alpha, which goes from X to real lines. So here maybe we should mention that defined almost everywhere. So I hope everybody understands what does it mean almost everywhere. It means that it's a complement of measure zero subset. Such that the composition UA U inverse. So this is an operator which acts in that Hilbert space. So if we apply it to a function f on x, it is the same thing as multiplication by alpha of x. For almost all x in. Okay, so that's a general statement, and we will illustrate this on a couple of examples. Example 1. So we have a position operator Q hat from L2 of R to itself, and I recall that it is just a multiplication operator, f of x equal x f of x. So it is easy to see that the measure space is just a real line with standard Lebesgue measure. And U is just the identity in L2 of R. So, and the alpha of x is just the identity map. So just nothing to do in that case because it is diagonal by definition. But things become more interesting if we take the case of momentum operator. P. So it's another operator which we defined last time, which goes as follows. P hat applied to f of x is a minus I h bar, derivative of f with respect to x. So here h bar just a real positive number. And now we see that it is not at all a diagonal action. And in fact, we can identify U as follows. So last time, in the third hour, you considered the Fourier operator. So consider unitary Fourier transformation operator. F, which goes from L2 of R to itself. And it is defined by its kernel. So I'm now switching to Dirac bracket notation. So this is just the integral kernel of that operator, which is E 2 pi I xy. So I refer to basic textbooks on Fourier transformation to say that this is unitary operator. And there is a specific normalization which avoids using normalization factors in front of. So it's a kind of very distinguished normalization which maximally simple. And what we remark is the following. So let us calculate the following things. So let us compose P hat with F. Then let us calculate the integral kernel of that. So which means that we have to calculate this. And I recall that in Dirac's notation, the definition of P hat is minus I h bar. So ket vector x applied from left to P is the same as a minus I h bar d over dx applied to ket x. And likewise for position operator, q hat applied from right to ket x is the same as x multiplied ket x. So now using this notation, so I can pull out P to the left, so which will be minus I h bar d over dx x f y. And now I can use the definition of the kernel. And then we have to differentiate this with respect to x. So we will bring down 2 pi I times y. And minus I will eat out the I. So the result will be 2 pi h bar y. And so maybe I can add here the conjugate version of that. Q is self-conjugate, so if we apply it like this, it will be also another formula. And we can use this formula in reverse direction, apply to y. So you see y times ket y. So which can be replaced by the left-hand side. So it is a 2 pi h bar x f q y. Now we have obtained the equality between two integral kernels. So now we can drop out the bracket vectors x and y to conclude that p hat composed with a Fourier transformation operator is the same thing as a 2 pi h bar of Fourier transformation operator times q hat. And this is very nice because using the, so uf is unitary, so invertible, we can rewrite it as a f minus 1 p hat f is equal to pi h bar q. And as we remarked in the first example, q acts diagonally, so Fourier operator does exactly what we want in the spectral theorem. So now we conclude that for applying the spectral theorem to p hat, so we choose space X again is R with the Lebesgue measure. As in the case of Q, and U, which is is chosen as the inverse of the Fourier transform. And finally, it remains to identify the function alpha of x. Becomes just a linear function up to this multiplicative factor 2 pi h bar x. But of course, in general, if you have a sufficiently complicated self-adjoint operator, it's a difficult problem of getting those ingredients, this isomorphism of Hilbert spaces and the multiplication function. And effectively, the whole quantum mechanics is the story of diagonalizing self-adjoint operators. Because in physics, applications of physics in quantum mechanics are based on the choice of a self-adjoint operator, which is called Hamiltonian. And then the physical interest is the spectrum of that Hamiltonian, which is equivalent to realizing the spectral theorem for that Hamiltonian. Okay, so but let me continue with the third example, which is which generalizes the both examples simultaneously. So example 3. So we we start from a a version of the Baker-Campbell-Hausdorff formula. So we have for any operators A and B, we have a formula. So what we do, we take an exponential of A, and we conjugate by that exponential B. Then this can be expanded into infinite sum as follows. So we start with B plus commutator A with B plus 1 over 2 double commutator AB, A, and so on, plus generic term is 1 over n factorial, n tuple commutator A, and so on, AB. So n times, and plus up to infinity. Have you seen this formula before? Okay, very good. So actually, it is compared to Baker-Campbell-Hausdorff, this is much simpler, because so you can because to prove it is very easy. You just realize this as a left multiplication operator acting on B minus right multiplication operator acting on B, right? And after that, you just expand exponential into series and rewrite L and R of A in the usual way. This way you get the formula. So where LA acting on B is the same as the RB acting on A, which is AB. Okay, so effectively this is the proof of the formula. And then now what we do is choose a specific A and B. So for alpha in R, let A be equal minus I alpha over 2 H bar Q hat squared, and B is a P hat. So if we choose this operator this way, so what we get, E minus I alpha over 2 H bar Q hat squared P hat E I alpha. Okay, so let me, I will continue in a moment this formula, but let us calculate the commutator. So commutator is, this is a constant which we can pull it out, minus I alpha over 2 H bar Q hat squared commutator with P. And one more formula maybe of general nature. So if we commute product of AB with C, then this is the same as A commutator with C multiplied by B from the right plus A multiplies from the left the commutator BC. This is true for any operators. And if we use this, then this will be minus A alpha to H bar Q hat P hat commutator plus Q hat P hat Q hat. Okay, let us postpone this. So then we use Heisenberg commutation relation to get twice Q hat I H bar, right? And then we have some simplification of h bar and i's, and of 2. In the end, we just have alpha. And the choice of A and B is such that all further commutators are trivial. So consequently, A, B is 0 because A is proportional to Q squared, and AB is proportional to Q. So Q commutes with itself, so no further contributions. So the conclusion is that minus e to the power minus I alpha over 2h bar Q squared, which conjugates p hat I alpha to h bar Q squared, is equal p hat, the first term, plus the commutator, plus alpha Q hat. And now we can conclude that, now we can use the previous derivation for the position operator. So we can continue the left-hand side, E minus I alpha over 2h bar Q hat squared F minus 1 no, F. So we want to express P from here. So we should put F on the right-hand side. So F conjugates 2 pi h bar Q F minus 1 E I alpha to h bar Q squared. So the conclusion so for applying the spectral theorem, to p hat plus alpha q, we choose again x mu equal r dx, real line. The unitary operator u is given by inverse of that, right? So f minus 1 e I alpha to h bar q squared. And again, alpha of x is the same as before. Okay, so in this way, we see how to diagonalize any linear combination of the momentum and position operator. Of course, this is not a big deal, but still it illustrates the idea of the spectral theorem. Okay, and here we see that what we see here, we have used an exponential of a self-adjoint operator. Q is self-adjoint, so it's square. And we have a real multiplicative factor which doesn't spoil the property of self-adjointness. So we see here an example of a unitary operator constructed by using a self-adjoint operator, putting it into exponential. And now I'd like to give a general theorem of such correspondence. So we can always cook up an unitary operator from a self-adjoint operator by taking an imaginary exponential. So it is a precise functional analytic result. And let me just give you one definition of strong convergence in the space of bounded operators. So definition, a sequence of bounded operators AN strongly convergent to A if the limit of AN applied to V is equal to A applied to V for any V. So you know, when you have a normed vector space, then we have an induced norm in the space of bounded linear operators. And we can talk about the convergence with respect to that norm. But strong convergence is different. It is not the convergent norm convergence with respect to induced norm. Because we use the norm still in the vector space H, norm vector space H. And so we say that if the sequence of vectors obtained by applying the sequence of operators to any given vector converges, then we talk about strongly convergent sequences of bounded operators. So and with this notion, we can take an exponential of a self-adjoint operators. Now, for any self-adjoint operator A in a Hilbert space, we associate one parameter family of unitary operators. U sub index A of T given by E I T A for T in R. So the fact that these are unitary operators, this is not difficult by using the spectral theorem. Just think that we switch to the isomorphic space of L2 over some measure space where A acts by multiplication, then U of T is again action by multiplication, then the unitarity is just evident. But what is less evident is the following proposition. So the map UA, which goes from R to unitaries of unitary group of unitary operators of H. Here's a group of unitary operators on H. So the map is a strongly continuous homomorphism, group homomorphism, or continuous representation. Representation of the additive group. R. But the fact that this representation, it's not big deal, because the exponential, it satisfies the functional equation, but strong continuity. This is a more difficult part of, and I will not prove it. But the idea is using the dominated convergence theorem of Lebesgue integral. But just for your information, I give you this statement. And what is more even more non-trivial is a converse of that. So, which is known as the Stone theorem. Stone's theorem, which tells that the map A sent to U sub A is a bijection between the set of self-adjoint operators and strongly continuous group representations, continuous unitary representations of R into U of H. And again, for quantum mechanics, this is of great importance, this theorem, because as I say, the basic thing in physics is a Hamiltonian, is a self-adjoint operator, which characterizes a physical system. And then this exponential is what is called evolution operator. So the temporal evolution of the physical system is given by this unitary operator. And so it is a strongly continuous according to this theory. Okay, again, let us do an example. Maybe a couple of examples. And actually, you had one exercise of that kind for today, which is more complicated than the examples I was discussing here. So we have our favorite pair of self-adjoint operators, which are position momentum. So we have two unitary operators. And U sub P T, which is a E I T P. T in I. And so, of course, these are unitary due to the spectral theorem and so on, but in these examples, unitarity is seen just directly if we apply these operators directly to bra vectors following the Dirac's notation. So this is a E I T X X, and X applied to X applied by multiplied by T hat from the right. So we again using our rules, so we pull it to the right. IT minus I h bar d over dx x. So we simplify E t h bar d over dx, and here we have a shorthand notation for Taylor series, right? Exponential of the differentiation operator with a coefficient. This is just a shorthand writing of the whole Taylor expansion of a function, which means that the effect of application of this operator is the shift of the argument. And now we can just look at that definition and we see we can independently check that these operators are unitary just from the definition of the norm in the Hilbert space L2 of R. And of course, these are additive group representations, which means that we can, if we multiply them with different arguments, we have a simple multiplication rules. But what is more interesting, what happens if we multiply this with this? And that is known as a Heisenberg-Weyl commutation relation. So if we multiply U sub p hat of t with U sub q hat of s, then this is the same thing if we multiply U q hat of s U p hat of t. So that if we stopped here, that would mean that they commute, but they don't commute. And the correction term is a e power I h bar st. So this is known Heisenberg Weyl commutation relation. And referring to the previous semester lectures, so you have seen the quantum group. What is quantum group, right? The deformation of the universal enveloping Lie algebra. And the essential structural relation in the definition of quantum groups is this kind of commutation relation, where this guy is called Q. And so this way we see that somehow this commutation relation is built in the quantum mechanics very basically, because it shows up at such an early stage, just on the level of Heisenberg algebra. Yeah, and of course we can we can verify this either by using a Heisenberg commutation relation for PQ or just explicitly by applying both sides of the identity by using these two relations. So P hat is a result in shifting the argument, and Q is just multiplies by the oscillating exponential. So that's the left-hand side. And if we apply in the reverse order, then we get first EISX times bra x u sub p hat t, and then we end up with the same bra vector, but we lack multiplicative factor, which is exactly what shows up in the Heisenberg commutation relation. And the next thing is what happens if we put these two unitary operators all together. So if we define W of STU to be U sub Q hat of S, U sub P hat of T, E I H bar U. So yeah, if we define a three-parameter family of unitary operators like this, then we have a W of ST U times W of S prime T prime U prime is equal WS plus S prime T plus T prime U plus U prime, but not quite this. We have a correcting term here, which comes from exchanging U P hat of T with U Q hat of S prime, right? And that gives us here the correction term T S prime. So we get this, and you can recognize that this is nothing else but a unitary representation of the Heisenberg group. Berg group H3 of R of matrices so these are diagonal upper triangular 3×3 matrices of that form. So if you multiply matrices like this, you will get exactly this law of multiplication. Yeah, and so in particular, if this is G, then G minus 1 is minus T minus S, ST minus U. So this will be useful in formulas which I will write later after the break. Okay. Yes, so we just constructed a representation of the Heisenberg group, which is a group of upper triangular 3×3 matrices like this. And so the unitarity means that if we take STU conjugate, then it's the same as W of the inverse WSTU inverse. And then just by using the explicit form, we can check that we can bring, of course, you see, here we have the exponential given by Q hat put to the left, and the exponential with P hat put to the right. This can be anywhere, but when you take the inverse, then we take the reverse order, so we have to apply Heisenberg-Weil commutation relation to bring them back. So when we do all that, so we can check that the result will be minus T, and the U is exactly corrected according to the inverse matrix U minus ST minus U. But also we can see how it acts explicitly. So by using our formula, so the first U sub Q hat will give a exponential IXS. The second will give the shift of the argument. So the correcting exponential factor will give us just H bar U and the shift H bar. So that's the explicit action of the element of our family of operators. And we can, of course, take the conjugate of that. So this is W ST U star acting on X will be equal conjugate of that minus I XS plus H bar U X plus H bar T. So here we have the action of W minus S minus T, ST minus U acting on X by the formula over there. And now we can just rewrite this formula, so we can shift U by ST to remove this. So this is minus S minus T minus U acting on X is equal E minus I. So what we are shifting is U XS plus H bar U plus ST. Right? I just rewritten this formula by replacing U by U plus ST. then this becomes, this relation becomes this one. And now I can negate all STU to clear up the left-hand side. So WSTU x on x, ket vector x, is the same as E minus, now I have to be careful to change all the signs of STU. So S changes a sign, so this becomes minus XS. And I can compensate it with this minus. So I put here plus, I keep XS. U changes sign, but ST does not. So which means that I put H bar, U minus ST. And here we have X minus H bar. Okay, so, but yeah, this is a little exercise of how we manipulate this Dirac language. Okay, now we have a proposition which tells us that the representation W of Heisenberg group to unitaries of L2 of R is irreducible. And I would like to give a proof because it's a nice exercise of working with integral kernels. So let A, L2 of R, an operator. We can assume it to be bounded, a bounded operator, such that it commutes with our W family. A W S T U equal W S T U A. And by Schur lemma, if we can conclude that this relation implies that A is an identity operator, then this will be equivalent to irreducibility of our representation. So we use an integral kernel. So star is equivalent to X A W S T U Y equal X W S T U A Y. And now we can use our preparatory work. So you see, we encounter here WSTU applied to ket Y. So that's why we did this manipulation. So we write what we write. So we replace the underlined fragment by this combination. It suffices just to replace X by Y. So I write EI or YS plus H bar U minus ST X A or Y minus H bar T. So and now for the right-hand side, we can use that formula, just without any modification, EIXS plus H bar U X plus H bar T AY. And the element which depends on U is central, so it is a multiplicative factor, and we see that we can cancel it out right away in that formula because it is a common multiplicative factor. So what counts only the variables S and T. So let us use two particular cases. Two particular cases of that. So let me put this double star. So double star at S equals 0 is equivalent to what? So if we put S equal to 0, so we end up just with this. And equal to X plus H bar T A Y. And this is the same as X A Y equal X plus H bar T A Y plus H bar T. If I shift Y by T plus T, so I remove this term here and create it over there. And this is true for any X, Y, T in R. This identity. So it's a functional identity, not just for a given X, Y, T. And so what we can do here, we can, for example, choose in a specific way a variable T. So it implies that X AY, but the left-hand side does not depend on T. So we can say that this is equal A of 0. So the effect of our calculation, so this we can call it f of x minus y. So the integral kernel of our operator depends only on the difference of two variables. So we can put here equivalence because if the kernel depends on the difference, then this relation becomes identity. And now we can use another special case. Take double star with t equal 0. Then what we see, t equals 0. We have E I. What we have here, t equals 0. So ys x a y is equal E I x s x a y. Now this can be rewritten in a factorized form. So x a y multiplies E I x minus y s minus 1 equals 0. And this is equivalent by using this substitution that f of x E I x s minus 1 equals 0 for any x s in R. Right? So I substitute for the integral kernel function f of x minus y. But here I have x minus y everywhere. So I can rename it by x. And then this becomes the f of x e to I x s minus 1. All this product is equal 0. And using the fact that s is arbitrary, so we can now, for example, expand this into Taylor series. And then each coefficient of s power n should be vanishing. So this is the equivalent to say that f of x times x equals 0 for any x in R. Right? So this direction, it is evident. So as soon as you see, if you expand, there is no constant term because it is cancelled, then starting from first x, everything is vanished due to this, and vice versa. And there is a good exercise in distribution theory that this equation is solved uniquely. I mean that f of x is a multiple of delta function. Or this may be a complex number. So that's a conclusion about this calculation. And this is Dirac delta function, which we discussed last time. And you had some exercises for today. But what is the conclusion? We come back to what we started from. So we conclude that the integral kernel of A is equal C delta of x minus y. But delta function is an integral kernel of the identity operator. So the A is a C identity of in the space L2 of R. So that's irreducibility of our representation. So any questions? Everything is clear? Yes?
I guess I have a question. So, under what conditions is some self-adjoint representation of the Heisenberg relations integrable? So for the momentum or for the position representation that we looked at, we got the Heisenberg model.
Yes.
Commutation relations. So when do we get those? I guess.
Yeah. As soon as you have a self-adjoint Heisenberg operators, PQ, you have all these conclusions because you use just the spectral theorem, for example, for Q. And but there is a theorem which is called Stone-von-Neumann, which tells that this is a up to isomorphism unique irreducible representation of the Heisenberg-Well relation. So that's a good question. So let me put it as a remark. So Stone-von-Neumann theorem tells that any irreducible unitary representation of Heisenberg-Weil commutation relation is equivalent to W. So it's very strong. So as soon as you have PQ self-adjoint without any specification of its realization, but you know that these are both self-adjoint and satisfy the commutation relation, then you have uniqueness. And and then a remark, which will be important and at some later stage of our course, that according to Andre Weil, so it's spelled differently, so this is another person. The Heisenberg the W representation can be generalized to any contrarian self-adjoint locally compact abelian group A instead of R. So R is an abelian group, right? So, and it is locally compact with a R measure given by a Lebesgue measure. And essentially what we are doing under the name of quantum mechanics, we are studying the Hilbert space of square integrable functions over that group. And this remarks tells us that you can replace the real numbers by any locally compact abelian group, but with extra condition that it's a self-adjoint. This words here. So locally compact implies a R measure. So we have an integration. And so Pontryagin duality implies that the set of characters, which is given by f a to t, and the t is a group of complex numbers of absolute value 1, z in C, z absolute value 1, it's a continuous and the Pontryagin duality tells us that this is itself locally compact abelian group. Okay, so we so they kind of so the locally compact abelian groups behave similarly as finite dimensional vector spaces. and double hat is canonical isomorphic to A. That's what makes this theory similar to finite dimensional vector spaces. And only for finite dimensional vector spaces you have an isomorphism of the double derivative. And likewise for locally compact abelian groups. And then self-duality. There exists a group homomorphism, or homomorphism, or a group isomorphism. Exists a locally compact abelian group. So in this way, we get a Fourier, and consequently, we get a Fourier integration, Fourier transformation. Okay, just a Fourier kernel of x applied to y for any x, y in A. So if you replace A by real numbers, then all what is written here ends up with a Fourier conclusion is valid in that general context. And then you can define the W representation just universally in the space of L2 of A. So then U P hat of T, let me put it in the quotation marks, is defined on L2 of A as follows. So X U P hat of T is X plus T, X plus T for any xt, but this time everything lives in A, and UQ hat T X UQ hat T is acted with f of T, psi of T applied to X. And then we can go all the way to define the W and the corresponding representation of the Heisenberg group, analog of the Heisenberg group over that group A. Okay. Presentation of the metaplectic. And one of the reasons I don't know how to prove it, it's some long story to the group SL2R. So that's a rough explanation. But this doesn't explain why this central extension is given just by the group G2. That's what the difficult part of that statement. Okay, so what we do is the following. So we define group homomorphism H from G to SL to R as follows. So what we do is the following. So take a couple of operators, Heisenberg operators, P and Q. and put them as a row vector with operator valued elements. And then conjugate it pairwise by G. So this is by definition conjugation of the first component by G and the conjugation of the second component by G. And if you look at the definition of G, so it is a Fourier transformation. But this operator we did exercise in the first half. We've seen also that of course it commutes with Q, but changes P by a linear term in Q. So this is a linear combination row vector multiplied by 2 by 2 matrix H of G. So let us say why it is in SL2R. Then we just check that it is a SL2R for generating elements. So the first case, G equal F. Then we know that F Q hat F minus 1 is P, and the F what did we have? So F minus 1 P F was 2 pi H bar Q, right? That's what we had. And then if I apply, so this is equivalent to saying that F Q hat F minus 1 is P hat divided by 2 pi I H bar. And then if I apply once more F squared Q hat F minus 2 equal F P hat F minus 1 over 2 pi H bar, right? I conjugated once more, but F squared is a parity operator, right? So this left-hand side is equal minus Q hat because F squared is x plus y, not minus but plus. And from here we conclude that F conjugates P hat and gives so we should put here 2 pi H bar minus Q hat. And that is it. Now we can go to this formula. So F P hat Q hat F minus 1. So minus 2 pi H bar Q P hat over 2 pi H bar. And now we rewrite it as a multiplication of the row vector P hat Q hat with some 2 by 2 matrix. And what is it? So it is 0 minus 2 pi H bar, 1 over 2 pi H bar, 0. So we check that this guy is indeed in SL2R. And next thing is to apply our family. So second case, G equal E I P Q hat squared. And then G Q hat G minus 1, of course, is Q. It doesn't change Q. And if we conjugate P, then this what we did already. So it is a P plus 2IT Q hat times the commutator of Q hat with P hat. So it is a P minus 2 H bar T Q. So E I T Q squared P hat Q hat E minus I T Q squared. So it is a hat minus 2 H bar T Q comma Q. And again, it remains to rewrite this as a multiplication of the row vector P hat Q hat with a 2 by 2 matrix. And it is given by 1 minus 2 H bar T 0 1. And again, we see that this is a parabolic element in SL2R. And now G by definition is generated by those. So we just multiply the matrices, and so we get a group homomorphism. But the fact that it is a group homomorphism, it's easily checked from that definition. So if you take GH, apply, then you will see that H is a homomorphism. Okay, so I think it's a good moment to stop. And then, so the next time we will be now doing completely different things. So we will be studying a surface, punctured surface, and the representation of its group into group of PSL2R. So it will be a preparation of a symplectic space with symplectic morphisms, which is it? No, what was the second item in the plan? Maybe not this time. So I think that we will be doing some combinatorics of punctured surfaces first. No, not flat connections, but just combinatorics of triangulations. Sorry. Yeah, that's the same. But anyway, it will not be any more quantum. Thank you. Yeah, mapping class group and combinatorics of, yes, that's